In this video, we will do an optimization example where we maximize the area of a region. Okay, so I want to begin by just talking about what optimization is. So optimization, that word means to maximize or minimize, some quantity. Okay, so we've done maximization and minimization problems in the last section in 5.1. We talked a little bit about how to find absolute maxes and mins and how to find local maxes and mins. We're going to be applying those techniques, but to word problems now. Okay, so we're going to be looking at a lot of word problems in this section. And I know that that can be intimidating. Like, word problems can be a scary thing, but we are ready at this point. We are ready for these. Okay, so we're going to be dealing with the word problems. They can be intimidating, but we're ready for that challenge. So we'll talk a lot in this section about really breaking down these optimization word problems into steps. And one of the keys to doing that is being able to convert the words to math that we can work with. All right, so let's look at our first example. Okay, so this very first example, I also have written this example in a worksheet. So it's worksheet 9, problem number 7, if you want to refer to the worksheets. So here is just a quick copy of the worksheet. I'll post this on Camino as well. But it is problem number 7 from this worksheet. All right, so let me go back to the notes here. Okay, so let's read the problem and then we'll talk about how we can begin to solve it. Prison cells in Azkaban are rectangular, and they have 3 walls with one side open to the sea. So due to a surge in prisoners, the Dementors, so as an aside, Dementors are magical prison guards. So if you're familiar with Harry Potter, that's where this problem is sort of based off of. Azkaban is a magical prison in the world of Harry Potter. Okay, so due to a surge in prisoners, the Dementors split the prison cell into 3 smaller rooms by putting in 2 walls perpendicular to the side open to the sea. If the total length of the base of the walls in the new setup is 200 feet, what is the maximum possible area of the original cell? All right, so there are a lot of words there, but that's okay. Like, we really want to try to break down what this problem is saying. So I'm going to break these problems up into steps. So I'll really be explicit about all the steps in this example because it's the first one that we're doing. And then in subsequent examples, I won't list them all out, like step 1 and step 5 and so on. I'll just do the steps. So step 1 is we identify what quantity we are trying to optimize, which means to maximize or minimize. To maximize or minimize. Okay. So this question asked us, what is the maximum possible area? So it wants us to maximize, because it said maximum, it wants us to maximize the area. All right, and that's it for step 1. We've identified the quantity we want to maximize or minimize. We figured out, oh, it's the area, and we want to maximize it. All right, we are on to step 2. So step 2 is to draw the picture, if applicable, and assign variables. Okay, so what would sort of go in a picture here? So the problem mentioned that sort of the original cell had 3 walls, There's rectangular, there's 3 walls, and then one of the sides was open to the sea. So let's say that I'm going to make a dashed line here for the side that's open to the sea. So this side is open to the sea. There's no wall on that side. Okay, and then it says that the Dementors had to add 2 more walls that were perpendicular to the side that's open to the sea. All right, so we have to put in 2 more walls that are perpendicular to this dashed line. Okay, so the one thing that I kind of want to be careful a little bit is the problem doesn't say that those walls need to be equally spaced. So maybe, you know, one's like way over here, and then the next one's like pretty close to that. So not exactly an equal division of the space, but they don't necessarily have to be equally spaced. The problem didn't say that at all. So it's typically good if I don't assume that in my picture. Okay, so I have this picture, and then it says assign variables. So it might be helpful to assign a length to this side, for example. That's x. And if that's x, well, this is also x, and that would be x, and this would also be x. Okay, and then maybe for the other length, this sort of horizontal one, maybe I'll call that y. I don't necessarily know that x or y are the same, so I need to have different variables for them. But I do know these vertical lengths are all the same. They're all clearly x. All right, so that is it for step 2. We draw a picture when applicable, and we assign some variables. We are ready for step 3. So in step 3, now is where we really begin to do some math. We write an equation for the quantity that we want to optimize. And again, remember, that means that we want to maximize or minimize, depending on the context of the problem. And in this case, we want to maximize something. So we write an equation for the thing, for the quantity that we are trying to maximize or minimize. And this is a name. It's called the objective. The objective. Okay, so let's write down our objective equation here. So we wanted to maximize the area. That's what we said in step 1. So we need to write down an equation for the area. I'll call it A for area. So the area, and what did we want? Did we want the area of one of the smaller rooms or the entire original room? Well, the original problem said, what is the maximum possible area of the original cell? So we need to write down the area of the original cell, which is just going to be x times y. Okay. And we call this the objective. The way I think about it is my objective, it is my goal to maximize this in this problem. In a different problem, I might be trying to minimize the objective. But in this problem, I want to maximize this objective equation. Okay. So we've done max and min problems before, but typically when we've maximized or minimized something, our function was in terms of one variable. And right now we have area in terms of 2 variables. So we're going to have to deal with that. And that's what the next step is all about. All right, so we are ready for step 4. So step 4 is to get the objective. That's the equation that we just wrote down for the thing that we want to maximize or minimize. Get the objective in terms of one variable by using other info to write a second equation called the constraint. Okay, so let's talk about what this looks like. So let's try to write down our constraint here. So the constraint is some other equation that we can write down based off of the information that's given to us in the problem. So if I go back to the problem and go back to the picture a little bit, what other piece of information does the problem tell us that we haven't already sort of drawn in this picture? And how would I write an equation for it? So here I want you to pause the video for about 30 seconds and see if you can think about, what is that other equation I can write down? What piece of information did they give me in the problem that lets me write down a second equation? 4, 3, 2, 1, pause the video. Pause it for 30 seconds to think about this. It's really important that you actually pause the video this time, especially really think about this for 30 seconds. This is often the trickiest part in an optimization question, so I want you to start practicing thinking about that now, even in our first example. Alright, so hopefully you've done that. Hopefully you spent about 30 seconds thinking about what this other equation is, what this other piece of info that the problem gives us to get this second equation. And it turns out that second piece of info is, it tells us that the total length of the base of the walls in the new setup is 200 feet. So that means is, if we were to take all of these walls here, there are 4 vertical walls that each have a length of x. If we were to add up all those lengths, the x plus the x plus the x plus the x, and then also add up this other wall that has a length of y, all of those lengths should sum to 200. So this other equation that we're going to have, let's scroll up here, is that 4x plus y equals 200. So one thing that might be a little bit confusing is it talks about the length of the base of the walls. So this is harder to see with like a picture like this, perhaps. This is sort of like a top view of the picture. So imagine I had something a little bit more 3D-ish. Like if I had a wall that was sort of upright like this, and then maybe there's like another wall for the other side of the room, and here's another wall of the room, and then here's sort of like the front. Okay, so the bases are like this length, and this length, and this length here at the back, and that length over here, if that was just a straight up square room. So the problem is saying that, when you add up all of those base lengths, and that's the x, the x, the x, the x, 4 x's, and the 1 y, those should add up to 200. This is just a picture from top view. All right, so we have this constraint, and what I'm going to do now is I'm going to isolate one of the variables in the constraint, because if I remember my objective, our objective was the area equation. Area equals x times y. And we wanted this to be in terms of one variable instead of 2. And the way we can do that is if we can isolate one variable in the constraint and plug it into the objective equation, then we'll get the objective in terms of one variable. So it looks like it's going to be a little bit easier to isolate y. We get y equals 200 minus 4x if we do that. And now let's plug that into the objective. We get area equals x times, and y is 200 minus 4x. I can simplify this if I distribute the x a bit. We get area equals 200x minus 4x squared. So that does undo the factoring, but it is going to be easier to now do calculus on this, which will be our next step. Okay, so the reason why we're doing this is we like functions in terms of one variable. They're a lot easier to work with once we have them in terms of one variable. And that's the whole point of the constraint. It lets me substitute into the objective and get the objective in terms of one variable if it isn't already. All right, so we are ready for our next step, step 5. Now that our function is in terms of one variable, it's just a normal max-min problem. And we saw how to do those in the last section. We would begin by finding the critical numbers. So let's find the critical numbers. So we'll need to take the derivative. So the derivative is going to be 200 minus 8x. And then we find where the derivative equals 0 or the derivative is undefined. So this derivative, 200 minus 8x, that's definitely never undefined. So this never happens here. There might be other examples where it does. In this problem, it never happens. It's never undefined. So let's just worry about when the derivative equals 0. let's set 200 minus 8x equal to 0. So we get 200 equals 8x, and then dividing by 8, we get that x equals 200 over 8, which is 25. So we just have one critical number here, and it's x equals 25. Okay, so after we have found our critical numbers, we are ready for our next step, step 6, which is to test the critical numbers to see if they are, and so in this question, it wanted us to find the maximum possible area. In other optimization questions, it might want us to find the minimum something. But we know about two types of maxes and mins. We know about absolute maxes and mins. We know about local maxes and mins. This problem didn't explicitly specify one or the other. It didn't explicitly say the word absolute. It didn't explicitly say the word local. When that happens, it means absolute. Like when the question says, what is the maximum possible area? It means literally, what is the biggest possible area that we could have? And that implies it's talking about absolute, not local. Okay, so we are going to test our critical numbers to see if they are absolute. That's important. Absolute maxes or mins. All right. So there are a few ways that we can do this, and I want to kind of go through the few different ways. So method 1 is, what if the interval for our variable is a closed interval? Okay, so I'll explain what that means. Okay, so our variable that we got, the area in terms of ultimately was x. We reduced area, so it was in terms of just the variable x. And x in my picture, so if I just draw a smaller version of the picture here. Okay, so we had these two other walls that we had sort of drawn in. And these vertical lengths, we were calling them all x, 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 x. And then this horizontal length, we were calling y. Okay, so if we think about this picture, the smallest that x could be is 0 feet. We can't have x, because it's a length, to be a negative number. So I'm going to say x is always greater than or equal to 0. You know, realistically, it's a little bit weird to make a room where one of the lengths is exactly 0. If x was 0 feet, the shape we get is what's called a degenerate rectangle. So 0 feet leads to what's called a degenerate rectangle. Let me just write that here in the margin. It's not super important that you know that term. This is mostly just if you are interested. We get a degenerate rectangle. That's a rectangle where one of the sides is actually 0. Okay, and the largest, what's the largest that x could be? Well, the largest x could be, because the total length of all of these walls has to be 200, is 50 feet. If x was 50 feet, these 4 x's combined would add up to 200 feet. And that would mean that y would be 0. So if this happened, this would mean that y is 0 feet. And if y was 0 feet, we get another degenerate rectangle. Okay, so the largest x could be is 50 feet. And at these two extremes, at 0 and at 50, we get a degenerate rectangle, which means one of the lengths of the rectangle is 0. But that's a rectangle nonetheless. Okay, so we are using our closed interval method for finding absolute maxes and mins from section 5.1. So let's remind ourselves what that method involved. We plug the critical numbers and the endpoints into the original function, not the derivative, into the original function, which in this case was area. It was area equals, what was it again? It was 200x minus 4x squared. 200x minus 4x squared. All right, so let's do that. So we have to plug in 0, that was one of the endpoints. We have to plug in 50, that was the other endpoint of my interval. And we have to plug in our critical number, which was 25. All right, so if we plug 0 in for x, we get 200 times 0 minus 4 times 0 squared. And now let's just do the same thing with 50 and 25. Here we'll get 200 times 50 minus 4 times 50 squared, and plugging in 25, we'll get 200 times 25 minus 4 times 25 squared. Okay. So remember, this method involved plugging these values in, the endpoints, which were 0 and 50, and the critical numbers, in this case there was just 1, there was just 25, plugging them into the original function to see what's the biggest number that we get out, that's going to be the absolute max, and what's the smallest number that we get out, that's going to be the absolute min. So it turns out that when we work this out, this one is 0, when we plug in 50, that's also 0, and when we plug in 25, that is 2500. Okay, so we were interested in finding the maximum area, so we're ready to write that down. The maximum area is 2500. So the question wasn't asking for the dimensions of the cell, like it didn't want x as the answer or y as the answer. It wanted the area. And when we plug in x equals 25, we get that the area equals 2500. And there are units in this problem. The units of length were feet. So for area, there would be feet squared. And that is our maximum area. The very last part is to make sure we actually answer the question. So this question said, what is the area, maximum area? And we've written that down. Okay, so these values would correspond to the minimum area. And these make sort of realistic sense. Like, how would we get the area being equal to 0? Remember, we talked about that when x is 0, we have a degenerate rectangle. One of the sides is 0. And if one of the sides was 0, it makes sense that the area would be 0. Same thing when x is 50. When x is 50, y is 0, and we have a degenerate rectangle, and that has an area of 0. So that's where those are coming from. And this value is our maximum area. Okay, so although the question didn't ask for it, if it wanted the dimensions, I'll just put this in a little bubble. If it wanted the dimensions, we know that x equals 25 feet. And if we needed to figure out what y is, we could plug y into the equation that we had. We had our constraint equation, y equals 200 minus 4x. We'd get y equals 200 minus 4x, 4 times 25, which would end up being 100. So those would be the dimensions. X is 25 feet, y is 100 feet, and as a check, if we multiply those, we do get 2500, which is what we got for our area. Okay, so that is one way that we could test that our critical number was actually what we needed it to be. We needed it to be a max here. Okay, so there's another way that we could do this. So method 2, okay, so I'm giving myself a little bit more room here to write this. So method 2 is to use the first derivative test and some justification. So we'll get into what justification means, but let's begin with the first derivative test. So we learned about the first derivative test in the last section. So that involves making a number line and then putting any numbers that made the derivative equal 0 or that made it undefined on the number line. So that's just 25. That's the only thing that made the derivative 0 or undefined here. And then we make a sign chart of the derivative and of the original function. And we pick a test point in each subinterval. So something smaller than 25. Maybe I'll pick 0. And then I need something larger than 25. Maybe I think picking something like 30 is a little bit nicer computationally than 26. So I'm going to pick 30. Okay, so now we need to plug these test points into the derivative. If I plug 0 into the derivative, what was our derivative? So our derivative was, oh, here it was, 200 minus 8x. So 200 minus 8x, that's what I need to plug into. If I plug 0 into that, we get 200 minus 8 times 0, which is 200, that's a positive. Okay, so our derivative is positive here, which means a will be increasing. It will be rising. Now let's plug 30 into the derivative. That'll give us 200 minus 8 times 30. So this is 200 minus 240, which is negative 40. That's definitely negative. So that is negative, which means the original function a will be decreasing. So it'll be going down. Okay, so when our function changes from increasing to decreasing at a critical number like this, we already found 25 as a critical number. That means this is a local max. So a has a local max. Remember, this first derivative test was for local maxes and local mins at x equals 25, since we always got to say our justification for these. Since the derivative changes from positive to negative, so as a result, that means the original function a changes from increasing to decreasing. So the fact that it changed from increasing to decreasing is what gives us this local max here. But we've said before that in these optimization questions, we're not looking for local maxes and local mins. We want this to be an absolute max. Okay, so let's write that down and talk about, this is where the justification, remember for method 2, I mentioned we're going to use first derivative test and some justification. This is where the justification is going to come in. All right, so let's zoom it in here a little bit. All right, so but we need an absolute max. Okay, so there's a way that we can justify why this local max is actually an absolute max in this particular problem. So A has an absolute max at x equals 25, since it has something to do with specifically what our number line looks like. The only thing happening in our number line is a starts off increasing everywhere up until 25, and then it decreases the whole way after that. The only way for that to work is if 25 is not just the local max, it's the absolute max. Since, so let's write this down, since a is increasing for all values of x that are less than 25, and it's decreasing for all values of x that are greater than 25. The picture behind this is if I had my axes, and let's say this is where 25 is, and I have a point where 25 is, and this is my area function. The number line says when x is less than 25, a needs to be increasing. So my function needs to be increasing the whole way up until I get to 25. And I'm going to put an arrow. It continues in this direction forever. Okay, and then after 25, it says for all x values greater than 25, our function is decreasing. So it's decreasing the whole way after 25, and I put an arrow to indicate that it keeps going like this forever. The fact that it continues in that way forever means that this local max also just so happens to be an absolute max. This justification is essential. It is super important. Anytime we do one of these optimization questions, if we use this number line method, which sometimes we'll have to, we have to have this extra sentence to justify why it's an absolute max, not just a local one. Okay, so there is actually a third method for justifying why our critical number is an absolute max or a min. It involves using what's called a second derivative test plus some justification. So we actually don't know about the second derivative test yet for this, we need section 5.3 material, which is the next section. So when we do our optimization examples, I'm only going to be doing it using method 1 or method 2. But I point this out just so that you're aware there is another way that we could do these. Alright, so this was a long video, but in terms of our goals for this one, we've talked about how we can use our techniques for maxes and mins from section 5.1 to maximize or minimize things. Another way to say that is to optimize things. Okay, so a lot of the examples we're going to be looking at are word problem examples. Okay, and we've talked about how to determine whether a critical number is an absolute max or min. That was the last step about testing them. And we talked about two methods that we can use to test them. There was this closed interval method, and there was this other method using the first derivative test and a number line, but we have to finish that off with some justification to explain why is it not just a local max, why is our local max also an absolute max for this particular situation. So there are some problems that we're going to see where the interval for x is not a closed interval like this. And when it's not closed, we'll have to use method 2. So in the next video, we are going to do another example. That's basically what the rest of this section is going to be. It's all going to be just doing more examples.